So today in this video we will study a new topic, the closest distance of approach between two charged particles. Now this topic is very important conceptual wise and numerical wise for foundation for IITs, also for 12th class. Okay. So first of all, let us understand what is the closest distance of approach. Now let us say that we have two charged particles, both similarly charged, Q1 and Q2. Now let us say if one of the particle is fixed, let us say this Q2 is fixed and Q1 is moving towards Q2 with some velocity. Now as it moves towards Q2, we know that the force of repulsion will start acting as the distance between Q1 and Q2 decrease. Now this changes the kinetic energy of Q1 into potential energy. So the kinetic energy keeps on decreasing while the potential energy keeps on increasing as Q1 approaches towards Q2. Now at certain point, let's say at this point Q2, the entire kinetic energy becomes equal to 0. After this point, the Q1 particle after this point the Q1 particle will not go towards Q2 but it will repel from this particle. So this distance, we can say that this is the distance of closest approach, that is the two particles cannot be closer together than R0. So R0 is the distance of closest approach. So keeping this in mind, we will solve three cases. Case first is that suppose we have two particles Q1 and Q2. Both the particles are very far apart. Q2 suppose is fixed at its position. Both are positively charged. Q1 is moving towards Q2 with a velocity V0. At this point, let this be the point of closest approach. At this point, the final velocity of Q1 becomes 0. And from this point, the Q1 particle returns on its path. So let us say that this distance is equal to R0, the distance of closest approach. Now applying conservation of energy, initial energy equals to the final energy. Now the initial energy is the energy of Q1 when it was at this point. So at this point, all the energy that it has was only the kinetic energy. So that will be half mv0 square. At the point where V becomes 0, the kinetic energy of particle Q1 also becomes 0. So all the energy at this point is only potential energy or interaction energy, which can be given as K Q1 Q2 upon R0. Now as we solve this, we can find out that the distance of closest approach R0 will be given as 2K Q1 Q2 upon m V0 square. So this is the formula for distance of closest approach for this particular case. Now let us take another case. Let us say that there are two charged particles Q1 and Q2. Let this be Q1 and let this be Q2. Let the mass of Q2 be m2 and the mass of Q1 be m1. Let us say that initially the charge Q1 is at rest. It is not fixed, but it is at rest. The charge Q2 is moving towards Q1 with a velocity V0. Now there will be a point at which the repulsion between the two charges particles will be such that the particle Q2 and Q1 will start moving in the same direction with same velocity. Let us say this velocity is Vf. The Q1 will also have velocity Vf and it will move in towards right, and Q2 is also moving towards right. But because let this be the distance of closest approach. Why is this the distance of closest approach? Because at this distance the repulsion between Q2 and Q1 will increase and the R0 will also start increasing. The R naught will also start increasing. Both the particles will move in the same direction, but their velocity will change because of repulsion, and R naught will increase. So this particular case, at the point at which the both particles have same velocity, that distance we will call distance of closest approach. Now, using conservation of mass, we'll do it on next page. Using conservation of momentum, not mass, the conservation of momentum, we can say that m2 v naught equals to m1 plus m2 vf, because both the particles are moving together. So it will be m1 plus m2 into vf. Now from this we can find the value of vf to be m2 v naught upon m1 plus m2. Now by applying conservation of energy, half m2 v naught square, when the charge q1 was at rest and q2 started moving with velocity v naught, this is the initial energy of the system. This will be equal to the kinetic energy of the combined mass into vf square plus the potential energy between the particles. Now putting the value of vf here and solving it for r naught, we can find out that the value of r naught is equal to 2k q1 q2 m1 plus m2 upon m1 m2 v naught square. So this will be the distance of closest approach in this condition. Now let us quickly go to case 3. In this case, let us say that the two charged particles q2 and q1 are far apart initially. q1 suppose is fixed and q2